Hi, I'm recording this for my MECH 3409, assignment 1, question 2 and 3. And my name is David, and my legal name is Duojiali. My student number is 217-157-546. And here's my student card. It has my name and student number here. And I also have my driver's license. You can see the names are matching. And here are my pictures. Let's start solving problem 2. So in this case, because my student number, the last two digits of my student number is 46, so xy is 46, and I can use this to find the distance of each section, which is 34.67, and also one of the belts for pulley C. The force is 5.3 kilonewtons. And then let's move on to part A. So in part A, we need to find the tensions on the belt for B, because we know for the belt, there's one loose and there's one tight, and we're given that the loose one is has the 26% of the force of the tight one. So we can write that T1 equals to 0.26 of T2. And then we can write a torque equation. The sum of torque is 0 because everything happens is at the equilibrium moment. So that the force times the distance is from the surface to the center, which is the radius of the pulley. And then this is for pulley B, and this is for pulley C. And then we can also rewrite T1 as T2, which is 0.26 T2. And then now the only variable in this case is T2, so T2 is 8.9 kilonewtons. And after we find T2, we can use this relationship here to find T1. So T1 equals to 2.3364 kilonewtons. And that's the answer for part A. And for part B, we need to find the forces at A and D, which is the two support point. But before, we need to find force at B and force at C. So for pulley B, all the forces is the sum of two belts, the tensional force from two belts, which is 11.33. And for the pulley C, the sum of two belts, the sum of forces on two belts is 6.8 kilonewtons. So now we can use the moment equation. Because at equilibrium, so the sum of moment is 0. The moment is force times distance. So our center, which is moment A at A, is 0. So that we just need to use the force at D, for example, times the distance between D to A. And then minus the force, it's minus because the force C is pointing down, so it's minus the force C times the distance between C and A, which is 69.34, and then plus because force B is pointing up, times the distance between B to A. And then the only variable in this case is the force at D, so we can solve for FD, which is 0.7566 kilonewtons. So now we have FB, FC, FD. The only force that we don't know is the force at A. So we can write the sum of force equals 0 equation again because it's at equilibrium. So FA plus 11.33 is pointing up, it's positive, and then minus 6.8 is pointing down, so it's negative, and plus the supporting force at D, which is 0.7566. So we can find FA equals to negative 5.29 kilonewtons. So that's the answer for part B. And for part C, we need to find we need to draw the shear force diagram and the bending moment diagram. But now we need to do it section by section, so we can draw the whole thing, which is here is A, B, C, and D. So we are starting from negative 5.29 from A, and then there is a positive 11.33 kilonewton force from A to B. So negative 5.29 plus 11.33, we have 6.04 kilonewtons at B. So at this point. And from B to C, we're experiencing a downward force of 6.8 kilonewtons. So at point C, it will be 6.04 minus 6.8, which is negative 0.76 kilonewtons at C. And then for D, it's from C to D, it's a positive 0.76 kilonewtons. So it adds up to 0, which is what we want. And then let's move on to the bending moment diagram. So for bending moment diagram, we also need to do a section by section. This time, the moment at A is our center, right? It's 0. And then for the moment at B, we need to use the force at A times the distance of A to B. The force at A is negative, and A to B is 34.67 centimeters. So we have MB equals to negative 183.404 kilonewtons times centimeters. And then from B to C, we need to use force at A times the distance A to C plus force at B times the distance from B to C, which is 26.0025 here. And then finally for D, we just need to add up everything. From force at A times AD, force at B times BD, force at C times CD. And it adds up to 0, as you can see here. And that's what we want. So let's move on to part D. For part D, it asks me to find the maximum bending moment. And it can tell from the graph, right? The maximum point here is point C. It has the largest number, which is positive 26. So now everything we're gonna focusing on at point C. And then we need to find the bending stress at point C. So bending stress at point C, we can find that we use the equation to find it. So the 32 over pi d cube is the equation, and the moment at C, we also have it from previous equation, which is 26.0025. So we can easily calculate the bending stress at C, which is 0.0785 kilonewtons per centimeter square. The unit is because for the 26 is kilonewtons times centimeter, and the 15 is also centimeter, but it's cube. So the centimeter is cancels out one of them, so it's kilonewton per centimeter square. And the 15 is the diameter of the rod. And then for the torsional shear stress, the first thing is we need to find T, because we don't know T. So the T is the force times the radius of the pulley C. And we have this equation for part A, and then the answer is T equals to 266 kilonewton times centimeters. And now we have T, we can sub this back to the equation here. And again, D is the same thing, it's also 15, it's given in the question. It's the diameter of the rod. And then we can just calculate the torsional shear stress at C, which is 0.401 kilonewtons per centimeter square. It's the same unit. And here's the answer for part D. And then we can move on to part E. So for part E, we need to find the principal stresses, which is the maximum and minimum stresses, normal stresses, and also the maximum shear stresses. We need to use a Mohr circle in this case, because here is the center of the circle, and here is the radius of the circle. And we need to find this point and this point. Here is minimum, and here is maximum. So right now we have everything, so we can just sub everything back to the equation. It's all about point C. And we know here is 0.0785, here same thing, and the shear C is 0.4041 square. So we just, here is plus and minus, so it will give us two answers, one is minimum and one is maximum. So the maximum is 0.4422 kilonewtons per centimeter square, and the minimum is negative 0.3637 kilonewtons per centimeter square. And for shear stress, we use the equation that the large number of the normal stress minus the minimum number of the stress, because they are both negative, because minus a negative thing is plus, so just 0.4 plus 0.36 divided by 2, which is 0.4. So here is the maximum shear stress. And I think that's it for this question. And thank you very much for listening and watching, and have a nice day.